Object-oriented programming. You've probably heard it called OOP. It's, without a doubt, one of the most influential, dominant, and, yeah, controversial ideas in the entire history of software. For decades, it's been the bedrock of our digital world, but today, well, today, it's at a serious crossroads.
So, here's the paradox we're going to dig into. On one hand, OOP is the architectural foundation for countless systems you literally can't live without. But on the other hand, it's facing this growing wave of criticism from the very developers who use it every single day. It's a real paradigm paradox.
And this quote, it just nails the biggest complaint. It's from Joe Armstrong, the creator of Erlang, and it perfectly captures that feeling that OOP and its search for perfect structure often just saddles you with this crushing weight of complexity. You just want one simple thing, and suddenly you have to drag this entire complicated structure along with it. Which, of course, brings us to the big question, right? If it's so flawed, so complicated, why does it run the world? How did this supposedly clunky paradigm become the default choice for the software that you and I rely on every single day?
I mean, the reality is you just can't deny its influence. We're talking about the operating system on billions of phones, the productivity suites that run global corporations, the frameworks that power these massive enterprise systems. OOP's legacy is literally written in the code of our modern world. But to understand why, we got to go back in time, back to the problem it was designed to solve.
To really get why OOP took over, we have to rewind the clock and look at the world before it even existed. You see, the software world was staring down a crisis of its own making, what we call a procedural crisis. As programs got bigger and bigger, the way they were being built just stopped working.
In the early days, programs were basically just a long list of instructions. But as they grew, they turned into what developers call spaghetti code, a tangled, incomprehensible mess. The biggest problem, though, was that critical data was just floating around in global variables. That meant any part of the program could change it at any time. A single honest mistake in one tiny function could corrupt your data and cause a total system meltdown in a completely unrelated area. Debugging this stuff, it was an absolute nightmare.
And this was a totally different way of thinking. See, procedural programming kept the data separate from the functions that used it. But OOP came along with this revolutionary idea. What if we bundle the data and the functions that operate on that data together into one self-contained unit? This object would be responsible for protecting its own data. It was about bringing order to all that chaos.
This brand new way of thinking was built on four incredibly powerful concepts, what we now call the four pillars of OOP. These are the core principles that offered the solution to that whole procedural crisis.
Encapsulation, abstraction, inheritance, and polymorphism. Now, these aren't just buzzwords to throw around. They're a set of design philosophies that work together to help you build software that's robust, flexible, and way easier to maintain. Let's break them down.
All right, first up, encapsulation. This is the big one, the foundation. Think of it like a protective shell. You know, when you drive a car, you use a simple interface, the steering wheel, the pedals. You don't reach in and mess with the fuel injectors directly. Encapsulation does the same thing. It hides all the complex inner workings and gives you a safe public interface, which prevents the kind of data corruption that was so common in procedural code.
Now, building right on top of that, you've got abstraction. This is all about hiding the messy details. You focus on what an object does, not how it does it. It's just like your TV remote. You press volume up, you don't need to know anything about infrared signals or circuits. It just works. This lets developers use complex components without getting bogged down in the details.
Okay, next up we have inheritance, and this is all about not reinventing the wheel. It models what we call an is-a relationship. Think about it. A poodle is a dog, so it inherits all the basic things that make a dog, but it adds its own unique poodly features. In code, this means you can write common code one time in a parent class, and then all the child classes can just reuse it. It's incredibly efficient.
And finally, polymorphism. It literally means many forms. And honestly, this might be the most powerful pillar of them all. It's the ability for different objects to get the same message, but respond in their own unique way. So if you tell a circle, a square, and a triangle to draw, each one knows exactly how to draw itself. This is what makes systems so incredibly flexible and easy to expand later on.
So, armed with these powerful principles, OOP didn't just solve the procedural crisis, it went on to build an absolute empire. Let's just take a second to appreciate the sheer scale of its success out in the real world.
And seriously, the proof is absolutely everywhere. Google's Android OS, Microsoft's entire .NET framework, Netflix's global streaming platform. These are colossal systems, and they are all fundamentally object-oriented. They use these pillars to manage complexity, to let huge teams of developers work together, and to scale to millions, even billions of users. To really get the impact, just look at Netflix. Their goal was 4 nines of availability, 99.99% uptime. And they got there by using OOP principles at a massive architectural scale. Each one of their 700-plus microservices basically acts like a giant object. It encapsulates its own data and logic. This modular design gives them incredible fault isolation, making the entire system unbelievably resilient.
But, and there's always a but, despite this incredible success, the story doesn't end there. That empire has some serious cracks in its foundation. We're now living through an era of deconstruction, where the core ideas of the paradigm are being seriously reevaluated. And here's the kicker. It turns out some of OOP's best features are also its biggest weaknesses. Take inheritance. It creates this incredibly tight bond between classes, so a seemingly safe change in a parent class can ripple downstream and cause totally unexpected failures in all of its children. This is the infamous fragile base class problem, and it's a huge reason why inheritance can lead to systems that are just rigid and brittle.
This is what's really opened the door for other ideas, especially functional programming, or FP. The fundamental difference is how they deal with complexity. OOP tries to manage changing data, what we call mutable state, by locking it inside objects. FP says, let's just avoid changing data altogether, and prefers what's called immutable data. In today's world of multi-core processors, FP's approach makes writing concurrent programs so much simpler and safer.
So, what's the bottom line here? It's not that OOP is dead or useless. Not at all. Instead, it's undergoing a kind of deconstruction. Its best ideas, things like encapsulation and polymorphism, are being kept and absorbed. But its most flawed ideas, like that rigid inheritance we talked about, are being left behind. We're moving into a multi-paradigm world where smart developers just pick the best tool for the job.
Which brings us to one last big question. Is object-oriented programming dead? Or is it just being carefully taken apart, its most valuable, timeless components being used to build the foundation of whatever paradigm comes next? It really seems like OOP isn't dying, it's just becoming spare parts.